So for now, let us quickly resume our discussions on the torus amplitude. Since Ronak is going to take most of this class, we won't go very far this class, but I'll just at least set up the basic ideas. Maybe try to do the analysis of the closed. Okay, you might remember last class when we had a final formula. A final formula for the for torus amplitude. The final formula was just insert B0, B bar 0, C0, C bar 0. Just insert that. Insert those. And then make every vertex operator integrated. Okay. d2z by 2 pi squared 1 then 1 and so on. Okay, and then the straight sorted there. That was the final formula for vertex operator insertions. And you note that this formula makes sense even when there are no vertex operators. Okay? Our derivation of it doesn't quite make sense. But there's another derivation that at some point I will quickly outline, which can be used, which also works in the case that there are no vertex operators. So for the rest of us, how can we just assume that this formula continues to work even in the absence of vertex operator insertions? So the first question I'm going to ask is, what does it mean to compute the torus amplitude in the absence of vertex operator insertions? Okay? The vertex operators represented string states coming in or going out. So if you have no vertex operators, you're doing a torus amplitude with no string states coming in or going out. Okay? And so what you're doing is just vacuum torus diagrams. Now what's the field theory analog of that? The field theory analog of that is torus diagrams, circle diagrams, just bubbles in field theory. Okay? Now what do these bubbles, and this is of course one loop bubbles, you can have more interesting no insertion bubbles. But there are these sets of graphs in field theory that one can compute. And what do they calculate? Well, the partition function, and what physical information do they? The vacuum energy. Okay? Because the partition function is simply trace of e to the power minus beta h in the limit that beta becomes infinite. So we not put answer. So what you're going to get is time times the energy, but the energy only we've got this trace, but only the lowest energy state contributes. Since beta is infinite. So what we're going to get is minus beta times the vacuum energy. Okay? Now since the vacuum energy is really a vacuum energy density, what you really get is the space-time volume times the vacuum energy density. Okay? So in quantum field theory, these set of graphs could be used to compute the vacuum energy. Now in a quantum field theory, whether this computation is meaningful or not is a bit moot. Okay? Because the 0 point energy, the energy of the vacuum, can be changed by just a shift. But in string theory, this calculation is physical, because string theory is a theory of gravity. Okay? So this energy is what the graviton operator will couple to. Okay? So what we're going to go through at the moment is the computation of this vacuum energy. And as we move along, we're going to do this, that the actual computation, actual answer, will not be as important as the various features that we will see along the way. And many of these features we will, in our minds, generalize to include, will generalize to when you include vertex operator insertions, as you will see as we go. Okay? So we're just doing this calculation because it's by far the technically easiest thing to do. Okay? It has a physical meaning. Okay? But irrespective of that, it's by far the physically easiest thing to do, and it's just toy calculation that will show various features that will survive also with vertex operator insertion, as we will see as we I've been wrong. Yes.
And with the moment gravity couples should, it won't be a closed torus anymore.
It won't be a closed torus anymore. But you know what one could do is to look at the coupling of something like this. Suppose you have a diagram which is this torus times a very long tube and then something else. So then this will be an effective source for this something else, and this something else will include, for instance, there could be a graviton propagating in this tube. Okay? Hang on to the end of this discussion and it will become clear. Okay, we'll see in what sense gravity comes to this. This is a tadpole diagram. This being non-zero would give you a non-zero tadpole for the graviton vertex operator. That's the main aspect. I will try to explain this. Okay. Okay. By the way, there is a way of making this calculation even more physical. Okay? And that is to do this calculation with finite beta. Beta. I'm now talking about the calculation with beta infinite. But when you do the calculation with finite beta, this really just becomes a one-loop partition function of string theory. Okay, that's clearly physical. Now, how do we make beta finite? Well, we use the trick. We're doing Euclidean. When you're looking at a Euclidean spacetime, in order to make beta finite, all you have to do is take one circle and compactify it with length beta. That's another way of making it very clearly physical. Okay, it computes the full partition function, including excited states. This is also something we discussed. Okay, so with all these rough motivations in mind, which will become clearer as we go along, let us start studying this vacuum torus element.
So when you open the torus, it will be like a rectangular case. So in this case, what will be the time circle in this case?
No, we're not talking about the time circle on the torus. We're talking about the time circle in space-time. Okay, that's very important. There are two different constructs here. There's the world sheet and the space-time. The world sheet is a torus, and we have to integrate over all tori. Okay, I forgot to write that. It's formula. It's d2 tau by tau 2. That is the most important thing. Right? Okay, you remember? We were supposed to do the integral over all tori with the measure that we derived last time. It was d2 tau by tau 2. Tau 2 is the imaginary part of the torus. Okay? So, you should keep this distinction in mind, because when we actually compute the partition function of the torus, we will often do it by a trick, thinking of it as a partition function, with world sheet temperature, as you will see. So there are two different things. There's the world sheet and the spacetime. This beta is the periodicity of a circle in spacetime. So in order to do that computation, we will have to take spacetime and make one of the x's periodic. We'll discuss this. Okay, great. So let us proceed. Now, in order to do this calculation, we need to know a little bit about the torus, and then we need to know how to compute this expectation value. These are the two things we need to know. Okay, so first let's talk about the torus. In the last class, we had discussed that the torus was to be thought of as a lattice. Okay? And this lattice here had identification. One of the identifications was z goes to, that was the lattice of the complex plane, and z goes to z plus 2 pi, and the second one was z goes to z plus 2 pi tau. Okay? Let's think of, just to get a little intuition, if tau is purely imaginary, it's a rectangular lattice, because the second vector just goes up. Okay? And we had discussed in the last class that different values of tau sometimes give rise to the same lattice. One immediate identification was tau goes to tau plus m, where m is any integer. Okay? Can somebody remind me why this gives rise to the same, this change in tau sometimes called the complex structure of the torus. Can you explain to me why this change in complex structure is the same lattice? It's going to another lattice point. Exactly. So what we're doing is identifying the two-dimensional plane. What does lattice mean? It means Z is to be identified with m times Z plus m times 2 pi plus n times 2 pi tau. Okay. The torus is the complex plane modulo this identification. Now, this identification is true for all m and n, all integers m and n, positive and negative. Okay? Now suppose I take tau to tau plus some k. What is this doing? This is doing z goes to z plus m times 2 pi plus n k 2 pi plus n 2 pi tau. And just by redefining this to be m prime, because this identification is true for all m, just redefine that to be m prime, it's the same identifications. Okay? So, this is an obvious redundancy of this our description of the torus. Shifting tau by 2 pi by an integer. There is one less obvious redundancy of the torus. Okay? There is one less obvious infinite redundancy of the torus. And that's the following. Suppose you take tau goes to minus 1 by tau. Up to an overall scale factor, we get the same torus. That's my claim. Let me try to demonstrate. Is this clear? So, what I'm going to do is sway. You see what? The idea of this is that this new identification will be the same as the old identification once we flip the role of the first and the second lattice. Okay? So let's do that flip. So we had Z was identified with Z plus 2 pi and Z was identified with Z plus 2 pi tau. And with these identifications, the metric was dz, dz1. Now let's define a new coordinate W. The new coordinate W is equal to Z divided by tau. Okay? So let's look at what these identifications become. What do I mean by flipping? This will become precise. Hang on. Okay? So suppose we define a new coordinate W. The new coordinate W is defined as Z divided by tau. Okay? So, what are the identifications in the W? Okay? So, since Z goes to Z plus 2 pi tau, this tells you that W is the same thing as W plus 2 pi tau. Sorry, times. Yes. Pi tau. And also we get W is the same as W plus 2 pi. Now what's the metric in terms of W? In terms of W, the metric is tau bar from mod tau squared dW bar. Just substituting dz bar and putting z is equal to tau epsilon. Okay? So the metric in W remains flat after this conformal factor. If we are interested in tori only up to conformal factors, we can ignore this mod tau square. Okay, we can ignore this mod tau square, and we have that W goes to W plus 2 pi tau, and W goes to W plus 2 pi is our identification. Now, you see, if we've got identification by a lattice vector, any linear combination of that, we've also got identification by minus that lattice vector, and any linear combination of that. We use a convention in which tau. So this convention can always be used to set tau at a positive imaginary. We want to use that convention. So if tau had positive imaginary part, 1 by tau has negative imaginary part. Okay? So we just take care of that by flipping the sign of this. Yeah. I'm saying, see, what are these lattice vectors? This is just a basis of identifications. So if you identify by shift by a lattice vector, and any multiple of it, that's the same as identifying by a shift of minus that lattice vector, and any multiple. Okay, so in our basis, there are various redundancies. The lattice vector minus lattice vector give you the same torus. To fix that redundancy, what we do is adopt a convention. We will choose tau always to have positive imaginary. Because if tau had negative imaginary part, then minus tau has positive imaginary. Okay? So, the identification we got were this, but as far as the lattice is concerned, we could equally value flip the sign. And we need to equally value flip the sign if we're going to use the convention that the identification vector always has positive imaginary part. So, I'm going to do that. Okay? And now this is exactly the definition of a torus, but with tau parameter replaced by minus 1 beta. Okay? So you see that the tori tau and minus 1 by tau are actually secretly symmetries. Up to a confirm. Okay? This has all been very fancy, but let me work this out now for the special case of rectangular torus, where it becomes very clear. See, this is a rectangular torus, but this guy has length 2 pi and this guy has length 2 pi tau. What we do is now just flip axes. So should we do this as a rectangle? We got this as the x-axis and this as the y-axis. Okay, if you want to continue to have the right-handed system, we should really got this as the x-axis and this is the y-axis. So look at it this way. X, y. Now, blow this up, so this has length 2 pi. What will this have length then? 2 pi by tau. Okay, and then there's some sign. Yeah, that's the sign. You understand? It's just that the torus is characterized, in the special case of rectangular torus, is characterized by the ratio of the two sides. Ratio and 1 over ratio gives you the same thing. It's just a matter of convention about which one is this, which one is that. Okay, excellent. So now you see that this identification that we get that we have identification by tau goes to tau plus 2 pi and tau goes to tau plus tau goes to minus 1 by. Actually, if we've got these two, you can generate the larger set of identification. Tau goes to A tau plus B over C tau tau plus B. Okay? Tau goes to A tau plus B over C tau plus D, where determinant of A, B, C, D and A, B, C, D are all integers. Okay? This is the group called SL2. Now, very briefly, I'll tell you about some things that you can, these are some algebraic things that you can easily check for yourself. The first thing is that suppose I do one of these transformations and then another one. That gives you a compounding group. Okay? I do A, B, C, D and then A prime, B prime, C prime, D prime. If it's indeed true that this thing here is the most general transformation generated by my two moves. Then this ABCD and A prime, B prime, C prime, D prime should once again have generated some effective ABCD. Let's quickly check it out. So we have A times A prime plus A prime tau plus B over C prime tau plus B. B into nothing. C into A prime tau plus B over C prime tau plus D, and D into nothing. That's what the compounding is doing. Fine, thank you. Thank you. Okay? And now we just cross multiply out. So we get the whole thing is just divided by. So we cancel the denominator. Now what's the coefficient of tau prime here? Tau here. Okay. So the coefficient of tau there is A prime.
I think it's clear that you get one term is linear in tau and the other which is just a constant.
Yes, but I actually want to show you that it's matrix multiplication. Yeah. A prime plus C prime B times tau. Okay. Plus A B prime plus B prime B over C A prime plus C prime B tau plus C B prime into
D prime D.
plus B prime D. Okay? So suppose we call this guy A twiddle. Okay, so this guy is A twiddle, this guy is B twiddle, this guy is C twiddle, this guy is D twiddle. Then you see that A twiddle, B twiddle, C twiddle, D twiddle. Now it's one way or the other. I'm going to write one and just check. Either A, B, C, D times A prime, B prime, C prime, D prime, or the other. Other way around? Okay. So A prime, B, C prime, good. A, B prime, B prime, C. Yeah. Okay? So you see that this set of moves is closed, and in particular is generated by group action, the group action of matrix multiplication. Okay? Now, what were the two basic moves that we looked at that we argued physically were redundancies? The basic moves were 1, 1, 1, 0. Right? Because we wanted tau goes to tau plus 1. You see that will give you 1, 1, 1, 0? Because that's tau plus 1. Oops. Over 1. Okay? And we also tau goes to like A tau plus B C tau plus D. We also wanted tau goes to 1 by tau, or minus 1 by tau. Okay? So this matrix would do the job. It's minus 1, 1, 0. That would be tau goes to minus 1 by tau.
Why do we need to make this convention?
That's convention because of our, yeah. The convention was just that we wanted to deal with taus with positive values. It's not fun. Okay? And now you can easily convince yourself that by multiplying these two matrices an arbitrary number of times. So firstly, each of these matrices is of this form. Secondly, does these two matrices do have determinant 1? Have 1. Okay? Now you know that multiplying two matrices gives you the determinant multiplies. So both matrices have determinant 1, no matter how many times you multiply that, you get determinant 1. It's clear that this kind of matrix multiplication, you start with integers, you get integers. So it's clear that everything that you get lies within this SL2Z, and you can easily convince yourself that you can get an arbitrary SL2Z matrix by multiplying this sufficiently many times. Mod Z2, yes. Now, this mod Z2 is basically the following thing, that tau and minus tau generates the centaurus. Okay? So, if you want to mod out by, for instance, 1 minus 1, this would be one of the elements you could mod out by, which would just take tau to minus tau.
You also need an overall scale transformation.
Scale transformation. Yes, all of these will generate an overall scale. You want to know what the scale transformation is?
It's just a detailing that. Do these two generate SL2Z completely, or do you also need something a sigma change?
No. These two completely change. So, let's see. Okay, by the way, we're interested in SL2Z mod Z2 for the reason that he pointed out that apart, this group action doesn't respect the fact that tau and minus tau are the same torus. We want to put that in by hand.
This is related to the terms of the convention.
Yeah, that's related. That's right. That's convention. Exactly. Okay, great. Can I leave you to check that just these two moves give you all of SL2Z? Okay. It's really actually very clear. But anyway, I'll leave it to you. I'll leave it to you to check that. Just there. Okay. Fine. So, now, what now is the fundamental variable of on the space of complex structures of the torus? It's this tau, but tau is subject to this identification. Okay? And so when we are doing this integral over tau, we're not going to integrate over the whole complex plane, because that's been too much. Because we're integrating over an infinite number of inequivalent tau. We should just integrate over what is called a fundamental domain of this modular group. So let's find what the fundamental domain is.
So tau cannot be purely real because then it's degenerate.
If tau is purely real, this is a degenerate class. Yeah. So tau being purely real is a single. But of course you can approach it. That's, degeneration. One side much larger. Okay. Yeah. So now let's look at the tau plane. Okay. Let's look at the tau plane and see what we can do. In restricting to a fundamental. Okay, I want to make one nice choice of a fundamental. Okay, the first thing we can always do, we've already said that we can always take their path. Then, by tau goes to 1 by tau, minus 1 by tau, we can always make sure the modulus of tau is less than 1. Because suppose tau and modulus greater than 1, we take 1 by tau of that. Okay. So we can always stay somewhere inside the unit cell. Okay. Now, Now, moreover, we can do more. Okay. Yeah, sorry. Okay, I'm sorry. So, yes.
So,
Please.
but tau is actually a ratio of the two sides of the torus, is it not true? Ratio of the two periodicities, especially.
It's true. It's true.
So why can it not be the two period? Because if
Because this is a ratio as a complex number. So one guy is here,
yeah.
the other guy is here, you're not generating a two-dimensional lattice. You see, firstly,
Yeah.
You see, what you want to do is to generate some part of the plane. And then you're not making any identification here. What you've got is a bunch of lines. Right, let's suppose that we chose tau equals 1. Okay, that's generating this identification and the same identification. Okay, so it's only identified by one thing, that's not a problem. Now suppose you chose tau equals half. That's just ignoring the tau equals 1 identification. If you choose tau that is real but irrationally related to 1, you will be end up identifying essentially all points. You understand? This is some singular entity. Okay? But just, this is a very formal mathematical way of thinking. You should think of the torus as this with sides identified. This is identified with this. And this is identified with this. Clearly something singular is happening when you take this play. The strip is 0 here. You want two linearly independent.
Yeah, sure.
Okay. Yeah. So we could choose either to take tau less than 1 or tau greater than 1. Actually, we will choose tau, not tau greater than 1. That's the usual choice. Okay. Now, it is also possible to choose this.
What for resonance?
No, we're going to choose mod tau greater than 1. The exterior of this. Okay? Now, mod tau greater than 1 is a large space. Okay? It is also possible to simultaneously choose tau to lie between -half and half. The real part of tau to lie between -half and half. Okay? Now, what's the idea behind this? I suppose we could argue that there's sets of moves that will do this. You see, certainly it's possible to do these two things independently. Because it's possible to use tau goes to tau plus 1 to set tau between -1, half and half. And it's possible independently to choose tau goes to 1 by tau to set tau to be greater than 1. But what you might worry about is that, look, suppose I'm here. Okay? So that my tau was greater than so that my tau was greater than 1, then I use the move to set tau in here. Okay? That will violate my tau is less than, violate my mod tau is greater than 1. So can we do both together? That's not immediately clear, but it's true. I think just you could either check this by studying these matrices, okay, or probably just an infinite set of moves. What? You can do inversion of this point, but that might now take you again. But then you keep going. Exactly. I think that infinite set of moves will eventually bring you into this function. You have to argue that terminates, but I think it's probably visually clear. Anyway, you can argue this. It's true, and certainly with your just by playing these matrices, you can do this. Okay, so true.
So where is real tau map?
What?
Real tau.
Oh, where does real tau get mapped to? Yeah, that gets mapped to infinity. But how do you know this? Let's do real tau along the z-axis, along the y-axis. So what is this? It's a torus. Well, one side is much bigger than the other one. Okay? So then if you do 1 by tau, that will take you which further. Actually, yeah. If you come along some other axis, you will have to do many shifts after it. But it will always good. Always good, some extra. Yes.
But how is tau going to migrate for different from the other two moves?
Which two moves?
Like we had two moves, and then we said tau going to migrate tau. Yes, isn't it like how are they different? Tau goes to tau plus 1 and tau goes to minus tau. Like it's not the same thing, right?
It's not the same thing, it's a reflection.
No, it's different on the move, but it's doing the same thing. It's a part of the tau identification.
It's a part of the tau identification, but it's changing the orientation of the space. So,
like you use the first two guys to say it's SN2Z, and then you said you use the third guy to make it SN2Z mod Z2.
yes.
But I thought you used the three guys to make it SN2Z because they all look.
Wait, let me. So, I see. So this is what you were saying right at the beginning.
Maybe it is because any ABCD belonging to SN2Z, each and all ABCD, it still belongs to SN2Z.
Yeah, its determinant is not 1. That's true. So he said this body, just a minute, maybe I just said it's body. He has a point. I mean, his point is that if it's not an SL2Z, there's no sense in which you're bodying out.
The body out happens because in SL2Z, then
ABCD and minus ABC.
Yeah.
That's what I think.
Yes.
Sorry. This is what I think. I think he's right. See, suppose. Yeah, sorry, I said that. Suppose you have A, B, C, D, and you look at minus A, minus B, minus C, minus D. As matrices, these are different. Okay? Yes, thank you. I just said it. As matrices, they are different, but clearly they use the same identification. Okay, now what matrix changes this to this? It's minus 1 minus 2. Okay? This is minus of identity, it has determinant 1, but it's clearly a central element. Okay? Because it commutes with everything. Okay? So it makes sense to mod out by it because it's central. Yeah, so sorry, I just said this minus this. This. Yeah, sorry. Okay, excellent. Okay, so I'll leave you to check that you can always get to this region. Now, this region is sometimes called the fundamental region of the modular group. Oh my, the product being done. I'll stop it. Okay, we have to more or less look forward to it. So I'll give you a go. This region is sometimes called the fundamental region of the group, and what we are doing here is what we will do, our intent, our internal integral over is this fundamental region. Okay, this is clear. Excellent.
Why do you take starting with that tau not so is greater than something?
You can choose it. You see, doing what you want is to do the integral over any one region that such that no 2 points in that region are mapped to each other by SL2Z. Okay? Such that no 2 points in that region are mapped to each other by SL2Z, and that this region covers every physical torus. This is one choice. You could choose others. In fact, this turns out to be another choice. There's another choice that looks sort of like this, where this I would have to, it's some circle which I would have to. But there's another choice that is in this region. There's an infinite number of such fundamental relations. You make a convention to choose one. Okay, we're choosing this upper line. Fine. Okay. Now let's go. Okay. So now that we understand that torus really well, space of tori. Okay. Now that we understand space of tori really well. Okay. What we're going to do is try to evaluate this particle, the string particle. Okay? So, what we need to do is to evaluate d2 tau over this region, over tau 2, times the expectation value C0, P0, C0 bar, P0. That's what we need to do. Okay? So, in order to do that, what we need is the partition function of the conformal field on a torus of modular parameter. Okay? The partition function and in the BC for the BC particle together with these insertions. Okay? So let's first look at the matter part and then look at the logic. What we've got is we want to evaluate the matter conformal field, the partition function of the matter conformal field theory on a torus that looks like this. It's 2 pi, right? Okay. Let us first look at the case where tau was purely imaginary. Okay? Suppose we first look at the case where tau was purely imaginary. So then this is 2 pi, this is 2 pi tau. Tau, this length of this, so suppose tau is I at tau 2, and the height of this is 2 pi tau 2. That's the length of this 2. Okay? Now I want to evaluate this partition function by determining it, by finding an equivalent Hamiltonian expression for this partition function. But all of you know how to do this. See, this is we can think of this as space, and this is Euclidean time. Okay? Can you see that this is simply trace e to the power minus 2 pi tau 2 times the Hamiltonian of the theory on a circle of length 2 pi. This is simply the familiar identification of periodicity in the Euclidean time circle with beta, which comes from the fact that e to the power iht is given by by Lorentzian path integral of length t in the time circle, e to the power minus beta t given by Euclidean path integral of length beta. That's the analytical integral. Okay?
What is it where e to the minus z tau?
Minus 2 pi tau 2 pi.
What would have equally well said e to the minus 2 pi on this Hamiltonian circle of 95.
Exactly. Sorry? Oh, wait, I sorry, say that again. I don't think said this way. You could have said that. These are the same thing. That comes from modular embeddings of the partition. Please says that. Yes, we could equally well have said that. The fact that there are two possible interpretations, both give you the same answer. For a modular embedding conformal field. Okay? We'll discuss this. This is what gives rise to what's called currents. Determination, high temperature behavior and low temperature behavior. Simply by switching states in time.
But if we are restricting ourselves to a particular choice of fundamental domain, then that already puts a restriction on what values tau 2 can take. Here tau 2 has to be greater than
Okay. But his point is correct that this torus, just as geometrical object, has two different Hamiltonian modes. Okay. And the point is well taken, I'm just choosing one. You know, okay. Now, we want to now look at not just rectangular values. So suppose tau2 is equal to I tau2 plus tau. Okay? Now you see what do we do? What we do for this identification is to move along time over this Euclidean time direction and then translate. How much do you translate by? By tau1. What is the generator of translations in the space direction? Momentum. Okay? So the guy with both tau2 and tau1 is trace of e to the power minus 2 pi tau2h plus 2 pi tau1 p. Where p is the momentum. Okay? Now, all we need to know, or all we need to do is to remind ourselves what momentum and h are in terms of L0 and L0 bar. Okay? So up to factors of 2, which I'll match to get the answer right, you know, which one has the 2. Basically, h was equal to L0 plus L0 bar. And p was equal to L0 minus L0 bar. No. Oh, yes, yes, you're right. There's 2 pi I tau1 because translation by A is given by the operator e to the power IA. It's a unitary operation. P is a Hermitian. You're right. Okay. So now let's look at this object. So we say h is L0 plus L0 bar, p is L0 minus L0 bar. So this is trace of e to the power L0 into what? L0 gives 2 pi, let's put a 2 pi out here, I tau1 minus tau2 and e to the power 2 pi L0 bar into minus I tau1 minus tau2. So we write this as trace of, now we take it higher. So e to the power I 2 pi I tau1 plus I tau2 and e to the power 2 pi I probably minus 2 pi I tau1 minus I tau2. Okay? Because these factors of e to the power 2 pi I L0 appear so often, they're given a name. E to the power 2 pi I L0 is called Q. You know all these computations. Let's see. Anyway. So, e to the power 2 pi I tau. So this is tau. And this is tau1. So this guy is called Q. So this is Q to the pi L0. And then this guy is clearly the complex conjugate of Q. Because every time it's a minus sign. So this guy, of course, then is called Q bar. So Q bar here. Okay? So the the Hamiltonian interpretation of this object is trace of q to the power n naught q bar k. Pretty simple formula. Okay? Now, let us just very quickly compute this for pre-bosons and vector. We just have to take the trace over the whole Hilbert space. Hilbert space consists of two parts, oscillators and zero. Okay? They don't talk to each other, so we can take the trace separately. Let's first do the oscillators. Okay. You see, let's do the X1 oscillator. I have to do all 26, but let's do the X1 oscillator. So the X1 oscillator has, the X1 coordinate has an oscillator of frequency 1, and an oscillator of frequency 2, and an oscillator of frequency 3. Right? So the oscillator of frequency 1, what's its partition form? Bose's formula, some famous person's formula. I mean, it's clear, right? Apart from 0 point energies, which we deal with. Okay, the 0 point energy be very carefully computed. This minus 1 by 24. That's stuff. We'll put that in right at the end. But apart from 0 point energies, this is the vacuum. This is, when you expand this, is 1 plus q plus q square plus. This is the contribution of one excitation of the oscillator, two excitations of the oscillator, and so on. So far so good, but for oscillators of frequency 1, there's also an oscillator of frequency 2. That is 1 minus q square. There's also an oscillator of frequency 3, which is 1 minus q cubed, and so on. Okay? So, now we get all of these. Okay? We get all of these, but then we also needed the 0 point energy. For each x, we had a q to the power, I believe, minus 1 by 10. Okay. Now, there is a definition. Okay, and we have all of this to the power 26 because there are 26 different directions in which there are. Now let's get a couple of definitions. Q to the power 1 by 24 times product n is equal to 124, 1 minus q to the power n, has a name in mathematics. It's called an eta function. It's called eta function.
Upper one and 24?
1 by 24. Well, upper put everything.
Maybe.
Infinity is eta of tau. Okay? Now, this definition therefore, okay, this definition therefore tells you that we get one over eta of tau to the power of x. I just hope that I got this 1 over 24. Perfect. Okay. This was the partition function that came from the left moving oscillators. Of course, it's the similar thing from the right moving oscillators. And then there are the zero modes. So let's remember what the zero modes are. The zero mode action was, so what was the action for the string? It was 1 by 4 pi del sigma x mu del sigma x mu. Focus on zero modes, this becomes 1 by 2 alpha. So you do 2 pi x mu dot. Okay? Let's take any one of these x mu's. What is this? So this is the action for a non-relativistic particle of mass 1 by alpha prime. What is the spectrum of a non-relativistic particle of mass 1 by alpha prime? It's p squared by 2m and therefore alpha prime p squared. Okay? So the partition function from the zero modes, but of course this is the zero mode part which we divide by 2, because you put half to the left movers and half to the right movers. This is the full angle. So L0 H was L0 plus L0 part. Okay, so alpha prime p squared by 4. So we also want to do q to the power this, q bar to the power alpha prime p squared by 4. Okay, we want to do this integral dp. Now, for this purpose, it's nice to move away from this fancy q notation back to now. So remember that q was e to the power 2 pi I tau. Q bar was e to the power minus 2 pi I tau bar. These are both the same, and so we get e to the power minus 2 pi tau 2 is alpha prime p square by 2. Check that. I really need to be wrong. 2 pi into tau minus tau bar. So the factor of 2, that was 2 pi I, and x. Right? Okay, and this we need to do the integral dp. So that's just a Gaussian integral. Okay? And so the Gaussian integral gives you 1 over square root 2 pi tau 2, and then some factor square root pi. Alpha. Square root 2 pi. Controlling this 2 again. Okay? The main thing is that you get 1 over square root tau 2 from each 0 for pi. Okay? So the net answer from the matter sector, is now this guy has a I'll tell you questions we answer. Fact check. He gets, for each scalar, he gets 1 by square root of 4 pi square alpha prime tau 2 mod e tau tau. He will get this. It's fun. Okay. Wait for our 2 pi. Right? We have this 2 pi down. origami gets reduced by state. I know, right? It's that we made an elementary mistake. This trace formula is not this, it's not dp, it's dp by. Okay, so this square root 2 pi and this square root 2 pi cancel, but this 2 pi can be written as square root 2 format. That's what it is.
We are getting more factors when I know about the sphere integration.
Which sphere integration?
Omega 25 exactly.
No, this is
And the
a,
ND 26.
no. This is a Euclidean calculation. We're doing this for each Cartesian dimension. Okay, and then we raise the both into 26. Yeah, in many places, you see, in many places in actual computations of partition functions, I don't care about factors because it's very hard to keep track of all of them. But once you reinterpret a partition function as a trace, then it is possible to keep track of each factor. Because you see, the density of states for a free particle, normalized quantum mechanics, is dp by 2 pi. It's just a true statement. The 2 pi is meaningful. As you can check by looking at the particle on a circle and then decompacting it. There's a fixed measure given by quantum mechanics. All of you know it. This dp by 2 pi is a correct relation. So here, in this case, we could keep track of everything completely correct. That, by the way, will allow us to fix the overall normalization in the formula for the string partition component. As it says.
That body cut out should be that.
Should be the. Yes, thank you. Okay, so that's it for the computation with the computation involving just the matter fields. Why does Ronald take over now? We'll do the posts and the interpretation of this. That's because the course ends. So the course are going to cancel two of these. Two of these. We can take it. Where did you ask your question? Say it out. So here's a question to suppose.
The theoretic contribution that you made for a path integral, the particle function that we wrote, within that well-defined in
What analytical relation? We've got a partition function, we're giving it Hamiltonian interpretation. There's no analytical. So which maybe I understand.
you had some complex thing, right? I got even tau 1 plus tau 2. Now you said that okay, this thing can be interpreted as e to the power minus beta h plus some tau 2
Shift.
shift. Yeah, so this you're saying that this is just Hamiltonian interpretation.
Yes, just no analytical. That's the with complex stuff is what we do. Because it's identification after a shift.
I'm going to do the calculation for 4 graviton amplitude. So obviously we start with the sphere, put K1 here, K2 at that equals 1 into K2, that equals 3D, put K3, and let's put K4 sitting. Right? So that is, and obviously all of these guys have polarizations because these are gravitons. So I just call it E1 mu1 mu1, E2 mu2 mu2 so on. It's symmetric, traceless, but it's nice to keep mu1 and mu separate for reasons you see. first we do the ghost integration, right? So we are going to have C1, C2, C3, and that is going to be something else over here. So, mod Z1, 3 or something. I'll just figure out those in a minute.
If you write mod, then all the powers are 2.
My final answer is wrong. Please figure it out as you go. I wrote 4 modes here. Yeah.
And the powers are 2, right?
The powers are 2.
Because C1, C2, C3 is Z12, Z13, Z23, and then the same thing for the C1s.
Yeah. Right. So this is squared, but then so basically this is infinity power 4 because Z12 is 1. It is 1. Right, and your final answer is not wrong. You will be happy with this. Then you're going to have the e power I kix. So we're going to give you the interesting stuff. The thing for e power I kix is going to be one possible pairs over their this thing and similarly Z13 and K1 plus K3. Most of these rays become 0. And in the end we're going to be left with mod alpha prime K1 dot K4 into mod Z24 alpha prime K4. And this, we put K4 at some arbitrary Z. We just mod Z something to one mod 1 Z something. And I think if I wrote it right, it is minus alpha prime u by 2 using all the identities about squares and blah blah. So these are the 3 factors. We will come back to them in the end.
And just to say, in the Canyon computation, we have a shift, an alpha prime u by 2 plus some number, which goes over here because in this case these are masses.
Yeah.
So K1 dot K4 is K1 minus K4 the whole thing squared, plus K4 the whole thing squared, minus K1 squared, minus K4 squared. All those K1 squared, K4 squared are 0.
So this is all stuff. I think most of the stuff we've done before. Anyway, so now comes the interesting part. Because
Wait, and are you going to show us that the infinities cancel?
the infinities, yeah, we have an infinity power 4. All these infinities are going to be 0 for a reason of what? One second. Sorry, it was right. So look at what all will be infinite here, right? What all will be infinite here is anything involving a z something 3.
Yes.
Right? And so whatever I get is mod z something 3 because all of them infinity doesn't matter what's here into alpha prime k3 dot k1 plus k2 plus k3. Now k1 plus k2 plus k4 minus k3 this is 1. Where k3 squared is 0. Right? and we take the limit in the correct order so that this is 1 and not infinity.
And what about the than infinity over of that?
Infinity is for cancel later. We are going to get in the interesting part. So, now the interesting part is that if you remember every the pattern session you are going to have 2x, 2 bar x, and that these are these indices 1, 2, 3, 4 are insertion indices, not dimension indices, and suppressing our dimension indices. Okay. So we would have this guy, but these guys shift at the saddle point. So actually, it's actually going to be something plus fluctuation fee, right? That is something we calculated in class and just put in the number later. Okay. So there's basically 4 into 2, 8 of these guys. So that's around 256 terms. So yes. So yeah, we're going to have various contractions. So right. So basically you have something plus dou xi x1 tilde into something plus dou x2 tilde and so on. And then you're going to take this guy of it, expectation of it. So what can happen? You can either have these guys picked out, or you can have these guys picked out, and then you can have various contractions. Okay.
So you have 0, 2 or 4.
Yes. 0, 2, 4. Yes. This is also yes. Now is where I restrict to holomorphic part.
Right.
Because anti-holomorphic part will be the same thing with bars. So yeah. So there it will be 0, 2, 4 locations. And so let's look at the 0 first. Right. And the 0 guy is something I need to get it. The 0 guy we need to set out generally calculate. Simple. So the 0 guy is going to be some theta's and theta's and it's going to be j not equal to I, so this is 1, or j not equal to 1 in kj by kj by z ij j by z I j z1. Okay, so basically for 1 is 1 here, for 2 we will have 2 here and so on, right? So yeah, and these kj's I'm going to give them the index called mu. So what is the mu? Yes. What is the mu? Now we had mu1 already in the polarization tensors. So you will have mu1, mu2, mu3, mu4 here. Then contract with the left index in the polarization tensor. Anti-holomorphic will have mu1 into mu3, mu4. Then contract with the right index in the polarization tensor. It honestly doesn't matter what you put where. It's just rotational convenience because everything is symmetric in index.
This contract, this mu1 is this index on epsilon 1.
Yes.
Polarization going.
Yes. So we always wrote EI, mu I, mu I, right? And Whatever comes from the first particle is going to have a mu1, whatever comes from the second particle is going to have mu2, and so on. Yes, so that we made our notation nice. So let's simplify this first, because that makes things very democratic. So basically let's look at it for this guy, yeah? You have K2 by Z12 plus K3 by Z13 plus K4 by Z14. Okay? And what am I doing? This is equal to, now I'm going to write K4 as K1 K1 minus K1 minus K2 minus K3. And now we get this mu is going to contract with the By here, and because it's transverse to polarization is always transverse, so it will E dot K1 will be 0, we can forget about K1s. Okay? And so this is just minus K2. So we get K3. Okay, I don't want to do this. K3 upon 1 by Z13 minus 1 by Z12 plus K4 upon 1 by Z14 minus 1 by Z12. Okay. And then we can rewrite this as Z12 minus Z13 by Z13 Z12 So this is right now it's K3, Z32 by Z13, Z12, plus K4, similar calculation we use this. Z42, Z14, Z12. Now notice the pattern here. We were looking at something that came from the first graviton. So you have Z13, Z12, Z14, Z12. Okay, so you have ones at the first graviton. We messed around with K2 to move things around, so you're going to have 2 in the numerator and the second one we have 2's. And here we have 2's. Right? And now this is the free index 33444. 33444. Now I made you notice the pattern because now I can do the same game with KC, the same game with K4, and basically get the answer 1/3 of K32 Z32 Z12 Z13 plus K42 Z42 Z12 Z14 plus K43 Z43 So in our earlier calculations we had only 2 terms here, but now we have 4 guys, so 3 terms. Okay. So that is my done. Great. Now I will call this guy A1. And notice what index did all of this have. So mu1, this was mu1, this was mu1, this was mu1, this was mu1, mu1. Okay. Similarly, we have similar term for A2, A3, and A4. So the saddest point part of the integral. Wait, let me just. Let's just try to what I was being look for. We have pure saddle point.
this A1, A1 you obtain after multiplying all these
Yes.
four of them.
Yeah. A1 is just one of those.
Yeah, exactly. So the pure factor point term, one is there was a minus I alpha prime by 2 hanging around. There's four of them. A1 mu1, A2 mu2, A3 mu3, A4 mu4.
So you simplified one of the.
Yes. See, the other names will have a similar pattern. So if you do, you can just look at this and create A2 mu2. Wherever you see 1, put 2, and wherever you see put 2, put 1.
Applicate this. It will figure out.
I am going to in a minute. Literally right now. Because am I going to do it literally right now or not literally right now? I am literally right now. What are we doing? Right. So let's look at A1 mu1. Okay. That is. Oh wait, I want to keep this for reference. I am going to look at A1. Right. What you can see is like Z3, Z3, wherever you see a Z3 after you see a Z3 notice, so they cancel with signs. All my infinities are positive infinity by the way. It's 1 by 3 and okay. So you worry about signs, this is plus infinity and minus infinity, so minus K32, I'm going to write it here. Minus K32, 1 set. No, 1. They don't do 1. A42
Is it 1 or minus 1?
then 1, 2 and minus 1. Thank you. Yes, I did not make the way. Let's see what's next. Oh, there are no calculations here. Z42 is Z minus 1 and Z14 is minus Z. Now, we have, for whatever pathological reason, we always like 1 minus Z more than Z minus 1. So, I am going to observe the sign of this. K42. This weird symbol is okay.
Wait, what about the sign of Z12?
It went into making Z minus 1 after Z.
I
Z42 है.
Yes.
Z42 that's Z minus 1.
Yes, and
So
then Z12 was minus Z.
Right. Okay, I'm just going to copy it. I'm not doing this one. Plus minus K43 by Z. Now let's see if this makes sense. Because Z43 was a minus infinity, Z13 was minus infinity, so we're happy. Z14 is a minus Z, so minus Z. Now A2, let's write it in this form. 1/3 of A2, I'm going to use the algorithm I told you guys, replace 2 with 1s and 1s and 2s. Z31, Z31, Z21, Z23, yes. Plus K41. Is it clear to everyone why the algorithm works? Or does it take? K23, Z23, Z23, Z24. Right. I'll also write down A3 because this is an empty one. A3 today and this 1 and 2. So K12, Z12, Z32, Z31, plus K42, Z42, Z32, Z34, plus Z41, Z31. A4 I won't write because it's too easy. I have it, it's like, I'll write it as well. A2. Right. A2 where? Let me write down 5 equation and see if it works. A2, 7 equation. Z31 is plus infinity, Z23 is minus infinity. So when Z21 is 1, so minus K13, which K31 which I used to reverse the indices of K. I'm not entirely sure why I did that. Z41 is a plus Z, Z21 is a plus 1, Z24 is a 1 minus Z. We are happy. And I revert the indices again. Okay, one way over it is a revert domain. Okay, so Z43 is a minus infinity, Z23 is a minus infinity, you find Z24 is a 1 minus Z, and I revert indices by one sign. Right. Now A3, look at this, 3, 3, 3, 3, 3, 3. Infinity square brought below. Okay, if you remember, right in our prefactor we had infinity power 4. So between this guy and A3 bar, we are going to lose one infinity. At least for a side pointer. We have to worry about infinity again and again. So yes. And I'll just so let me just write down all the case. So if there are sign mistakes in these two, we are going to have to remove them because I don't see the point of going to the feature section. Anyway, so that's A1, A2, A3, A4. I'm leaving them there because now we've done the pure function. Right? So just that we are done. Yes. Go ahead. Power of 3 settings. What are power of 3? So there is it. Let me call this 131. So I use all the numbers here and I put it here. Put 3 power minus 4. Here we are.
So this term scales like momentum to the power 8. If you take this and it's the other side.
Yeah. Yeah, maybe number 8, this will be 4 to 0 and then into 4 to 0 and then scaling. So you have 8, 6, 4, 2 and 0. I said 4 to 0 because the contraction usually eta, it throws away the key. Okay? So, right, so what's the one contraction term? One contraction term. So you remember we had every dou x written as saddle point plus fluctuation. One contraction term is when we pick two saddle points and 2 fluctuations and then we contract the 2 fluctuations, right? So right, there's going to be so basically you're going to have all possible contractions and wherever you don't have contraction, you will put A's. And powers of 3 and alpha prime and all. Right, let me write powers of 3 and alpha prime directly. Okay, it's going to be alpha prime power 4, 6 power minus 4. And keep it here, those factors will turn out very nice. That's the one thing about calculation in terms of place. Okay. So, first thing is obviously going to be the prefactors. Prefactors are going to have 2 from the saddle point. So, minus I alpha prime by 2 squared. And 2 1 by 3 is because there will be 2 A's. So, 1 by 3 squared. And 1 I somewhere. Right. Into. So suppose let's first take the term where 1 and 2 contract. The contraction is minus 1 by 2 alpha prime by z. I'll remember the order in a minute. Theta 1 2. Okay. And this way on that side, no? Z 1 2 square. Oh, the order doesn't matter. Theta 1 2 means theta mu 1, theta mu 2. It's very hard to write mu 2. Into A3, A4. Okay. And so these terms are going to be generic, minus half alpha prime. So basically, the 3 factors are going to be alpha prime cube 6 power minus 2. Theta extra half. 2 power minus 3. Okay, right. 2 power minus 3, 3 power minus 2. I should write them separately. 2 power minus 4, 3 power minus 4. As you can see, the 3s are going to climb up in powers of 2 because you are losing 2 A's at a time. The 2s are going to climb, 2 and alpha prime are going to climb up / down in powers of 1 because you are losing 2 but then you are gaining 1. And the sign is always going to be plus. Always, because here the minus I power 4, it was minus I squared into minus 1. But then the next one will be minus 1 into minus 1. So, that's easy. So, right. Let me. And let's pick out an infinity.
So, what is theta 1 2?
Theta mu 1, theta mu 2.
What theta was what?
Theta is.
Metric. Okay.
Sorry. Okay. Here no, it's going to basically. Oh. The polarization. Yeah. It's going to basically dot the 2 polarization tensors. Yeah. So right, infinities. So in all these terms, either an A3 will be, either there will be A3, in which case you are going to have the same way we lost the infinities here. Infinity squared is going to split out, or like in the next term, we are going to theta 1 3 by infinity squared A2 A4. So infinity is again we are happy about. You see the better me all after. Okay. Theta 1 4. Right. I'm going to find out the infinities assumed to exist. A2 A3. So on, many of these, the 6 of these terms. What useful? And yes, they will matter in a minute. Now, so this is all the one contraction terms. So let us that's 2. There's 1 here. The reference. This is 2. Okay. I should write theta 2 3 theta 4 A1 A4 A3 A1 right. So this is all your This is your single contraction terms. Double contraction terms are next. You take around. You just have two double contractions. Either 1, 2 and 3, 4 can contract, or 1, 3 and 2, 4 can contract. Yes? So,
1, 4.
You have dot. No, either you have this, and you have either this contraction and this contraction. These are the only two contractions.
What about 1 with 3?
1 to 3. Alright, I hope I wrote that in my books. Anyway. Sorry, there's a minus there. So, yeah. First, let's do the things. Eta 1, 2, eta 3, 4. Eta 1, 3, eta 2, 4. Eta 1, 4, eta 2, 3. What does it have to use? Okay. And for contractions, you always get minus half alpha prime. So this is 2 power minus 2 alpha prime power 2. And infinities, again we have Z34 here. Right. I have made it. So we have Z34 here, that's an infinity. You're going to get 1 by Z34 squared. That's infinity. Some 3 has been cancelled, contracted always. And we need to put in factors of Z, which I completely forgot. Right? Because whenever you have a contraction, it comes with a 1 by Z of that. And so this will have a eta 14 is 1 by Z squared, because Z14 is Z and sign doesn't matter for squares. And eta 24 is 1 minus Z squared, and eta 34 is 3. And similarly here, 1, 2, so this will give you 1 minus Z squared and Z squared. Right. So now, what is the next step? Okay. Now we are going to have to add these guys up. And yes, add these guys up, multiply and integrate. Okay, it's hard. Let's see. First, we should look at the Z1 minus Z2. Right. So, I'm going to So to make life easier, I'm going to rewrite this in a particular order, where the lowest power of Z is on the left, and for equal power of Z, lowest power of 1 minus Z is on the left. I'll show you why. Basically, we are going to classify terms by powers of Z and 1 minus Z, right? And then we are going to integrate. There's a formula in Boltzmann for particular sorts of integration we need to do. And I think there are 16 integrations we should do. Not 16. 10 integrations we need to do this. Yeah. And I will show you in a minute why that's 10 and not 16. In fact, why there are, okay, I'll show you everything. Yeah. So, 1 by Z is equal plus 1 minus Z by Z A24 plus minus A23 1 minus Z to minus A24 plus A13 plus Z upon 1 minus Z minus K14 minus K12 plus 1 minus Z K24 plus Z into minus K14. Let's show you how I did. K12 plus 1 by Z K13 plus 1 upon 1 minus Z Right. So now we have to do a perpetual multiplication. The first thing first proposition I'm going to make is that you're never going to get a power lower than z squared. Here it's clear because there are no extra z's. Here look at 1 by z squared. It's coming with a2 a3. a2 a3 does not have any z in the denominator. Okay. Look at a1 a2 a3. Two of them don't have z in the denominator and two of them are just multiplied. So there's never be 1 by something lower than 1 by z squared. Okay. Similarly, there's never going to be anything lower than 1 minus z squared. 1 upon 1 minus z squared. And similarly, there's never going to be anything higher than z squared. Because z comes in the denominator here and nowhere else. Okay, and everything is linear. Either linear or 1 upon linear. And similarly, nothing higher than 1 minus z squared. Now, okay, so 1 we have z squared minus 2 plus z squared 1 minus z minus 2 1 minus z squared. Okay, and second point is that suppose in any term which is z power m1 1 minus z power m2 whatever you're going to have m1 plus m2 less than 0. This is also need to convince you. Look here. This thing is either z is so either if m1 minus m2 less than 0 means that you will have something like 1 minus z by z, but never 1 minus z squared by z. Okay. Got it. I got the order right. Did you order right? So you see, suppose you put 1 minus z in the numerator, z in the denominator. The power over z, 1 minus z will never exceed the power over z. Okay. To convince you, look at this term. Here, let's count powers of 1 minus z minus power of z. Here it's 0 and minus 1. Here it's minus 1 and 0. Okay. And similarly here, so this is the anomaly which is where it's 1. No, this is 1. And this is so 0 minus minus 1. And this is also 1. And this is the 1 minus 1. Right. This was 1. This was 2. Yeah, this is 2. This is 1. This is 1.
Minus 2. I thought you were going to numerator as 1.
Okay. Z power m1 by 1 minus z power m2 over 2 m1 plus m2. This is what I have written.
I thought you did z by m1 and 1 minus z by m2.
Alright, so let's do this for.
I thought you were saying net homogeneous.
Yeah. M1 minus m2, right. So basically let's use a green chalk and write on top because I'm getting too much information. So this is minus 1, this is minus 1,
Same.
this is 0, this is 0, this is 0, let us find the zeros. Good confidence 0. 1 upon 1 minus z is
Minus 1.
minus 1, 0, this is plus 1, this is also plus 1, no, this is minus
1.
1. This is minus 2, this is
Minus 1.
minus 1, and this is
Minus 1.
right. So what was the point? Right. So let's look at the.
You want to show that the net power is always negative.
Yes. So where are the positive x? Here and here.
Yes.
But here there is never a negative. Point is, there's one line where there's no zeros. And there's only one line which there are positive, and the positive is at most 1. Right? So no matter how you try, which term you take,
So what about A3 with A2?
A3 with A2 will come with a 1 by z square.
That's okay.
Yes, that was my next one. Yeah, so in the pure saddle point term, you're convinced that you're never going to that condition.
And A3 with A1 similarly comes with that.
Yes, A3 with A1 comes with 1 minus z square. So yes, and in the two contraction term, A3, A2, you would think, hey, look, 1 plus 0, 1. But then there's a minus 2 there. So done. A3 with A1, you might think 1 plus 0, but then there's another minus 2 there. So that's fine. So point is, this is always true. Though I mostly use this because beyond this point I just started using mathematics. Because even after this there are 10 terms, and then you have to look around what all is there in 10 terms, and basically you write it all out in mathematics, it's a whole screen. So let me tell you what I can. I'm not going to write down all the structures that come, but I will tell you what I can. So let's summon up these factors from back into the history when they belong. Okay. So we had a mod z over this minus alpha prime.
Ron, one question. There's a theoretical physics curriculum that I'm going to have to go for 3 minutes. How much more time? Would you need about 15-20 more minutes?
No, 5-10 more minutes. It's just a last step here. I'll show you
quickly.
Yeah. Okay. Sorry. Let me be as quick as possible. So you're going to our three factors were mod z power minus alpha prime minus u, mod z mod 1 minus z power minus t, where u equals alpha prime u by 2 and t equals something. And now we open Boolean some, I think it's some equation which tells you how to integrate dz z power something, z power something, 1 minus z power something, 1 minus z power something. Right? Okay. Okay, maybe I should just write. Let me just write down what we need. Okay, let me call it 2u. Right. So the z sum is minus u plus n1. These are the same m1 and m2 here, by the way. Minus u plus n1. N1 is the anti-morphic counterpart for m1. Minus t plus n2 minus t plus n2. Okay, and this is a product of gamma functions. It's 2 psi pi by pi into 1 minus t plus n2 into many constants. Gamma of 1 minus t plus n1. Yeah, so basically you're going to get a lot of gamma functions, and you're basically going to get terms which are like 2 gamma for 2 t in the denominator, something s, some by something s, something u by something.
Actually, I have a suggestion. Since now more or less you got the answer, what's now interesting is the interpretation of the answer.
Yes, I know that.
What? You?
I don't have it.
You don't have it. Oh, so maybe I can. What my suggestion is that since we should go for this colloquium, maybe you can take 10 minutes of the next lecture,
Okay.
and then I can take over with the interpretation.
Yeah, okay.
So let's stop now because anyway it's going too fast for me.
Yeah.
Yeah.
I'll just do this part tomorrow again.
Great. Just you can start with the
Yeah.
Thank you very much, Ron. It was very clear and very nice.